Welcome back. This is Xfixium, and welcome to the How to Make a Master System Game Using Devkit SMS tutorial series number 11. In this tutorial, I go over source code that affects entities used in the game. I go over basic position concepts like converting tile indexes into tile coordinates and vice versa. I'll go over some best practices when creating code for your game. And finally, I go over the concept of creating pre-multiplied values and using them in your code. Let's begin. Alright, we're going to now define the functions within our entity source file. First one is the entity increment timer. This is very similar to the common increment timer. Should believe it's somewhere over here. Yeah. I'm going to take essentially the same logic that was from the increment timer from the common source file, and we're just going to apply it in the same manner for an entity timer, which is a property of an entity. So same idea, we're going to put the index of the entity that we want to change the property of, or the timer of, and then we're going to also hand in the threshold we're looking for time wise, and when the entity timer for that particular entity based off of index, when that threshold is met, we reset that entity timer, and then we return 1 or true that we have met that threshold. Otherwise, we haven't met it yet, so we're going to keep increasing it until we meet that threshold. Set entity visibility. This again goes towards the visibility property of an entity, and this just sets if the entity is within the viewport of our game, and it could be in various states. This first conditional, we're checking if the game state is in a stage of some sort, or is in the stage or running the actual game engine. If it's not that, then it will always be in view, because the reason why we do this is the entities get reused in other areas of the game, not just the actual game logic or the game engine. We are also using those same entities for the cutscenes and the title screen and wherever else we may want to use them. So in those scenarios, when the viewport, when they're not within the viewport, we don't want the marker behavior that would normally be within the game. And that marker behavior is, when they're off the screen at the bottom or the top, instead of showing the graphic of the entity, whatever it may be, the ghosts, it may be, the players, whatever. Instead of having that behavior available, we want to turn off that behavior in those scenarios. So that's what we're checking here. We're going to check the game state. We're going to check if we're actually in the game engine. If we're not, then it will always be in view, and that basically dictates that we can manually set them wherever we want, the sprites that is, or the entity itself, without it having that marker behavior. If we are also auto-scrolling, so in the beginning of a stage, it usually scrolls from top to bottom. We don't want to have that marker behavior in that scenario as well, because we don't want to show those markers while we're scrolling from the top to bottom when things are in and out of view. So we're going to ignore that behavior again when it's also the other conditional is that it's an auto scroll. And then here we actually have the behavior of it being out of view at the top or out of view at the bottom. It's pretty simple. We're just looking at the entity vertical position or the Y position, and we're going to have an offset to that based off of the center of what a sprite is. And typically the sprites in the game if not all of them, are 60 pixels by 16 pixels. So we're going to have a little offset to that to check if it's less than the scroll Y. So is it above, the entity is above the scroll Y? If it is, then it's out of view at the top. We have those defines. And then if it's out of view at the bottom, so it's our scroll Y starts at 0, 0. So if it's whatever scroll Y is plus the entirety of the height of the viewport, which is 192 pixels or 24 tiles. If it's below that, then it's out of view at the bottom. So we're just setting some constants depending on where the entity is, and then we'll use this entity visibility within the actual entity logic for those certain types, like the player, or in this case it would be player 2 that might be off the screen, and the bonus and ghost entities. We want to know if they're going to be off screen, so we can show that marker, and this is the conditional behind it. And then if there's anything that wasn't applied here in the conditional by default, it will be in view at all times. Set entity move speed. This is just setting the base speed and the sub speed for an entity, for the given entity. So it's again by index. So whatever entities that we're going to change here, we're going to put that constant in there. So that, again, that constant was based off the define. So when we look at the indexer for that, so whatever index it is, we would feed this index into that argument, and then they would handle that entity. So whatever index is, we're going to look at whatever entity's speed, and we're going to look at the subspeed. So subspeed is the base speed, like I said, and subspeed is the fractional portion of the speed. So that there's a certain subtlety to the speed increase as the stages go on, and we'll see that when we code the player and we code the ghost entities, and how that can change through each stage and all that business. Typically, I do not like to have more than 2 arguments in a function, so I don't like to hand over more than 2. Usually 2 is the maximum, so index and speed would be the acceptable approach in most cases. But when it comes to when I load things, I only really have that hard fast rule for this when it's not a performance situation. So when we're loading data before the game engine starts, or when a game state starts, it doesn't have to be as performant. So I typically will allow more than 1 parameter, but it's been said, and I've read documentation based off of SDCC, or the some of the to-dos, or what's good to do, or what's best practice based off what Sverks has said, and the creator of Devkit SMS, that you want to limit it to 2 parameters coming in. And again, that's to keep the code performant and run, or give it the best chance to run speed-wise. But here, this is going to be something that I will load at certain times of the game. It won't be running in the game engine continuously through the loop. So that's what and so basically we're handing in the index for the entity we want to change the speed and subspeed to, and then we're just handing in the speed and the subspeed, which are both cars. Get entity move speed. So what this does, we hand it a index, an entity that we wish to change or to keep up on the actual accumulation of the entity's subspeed. So, and it returns a car. So we return if we actually incremented the speed in some way. So it's typically what we would do. So first we got the actual base speed of the entity that we're handed. So we have that speed, so whatever it may be. Typically in this game, it's 1 or it might be 0 if it's if a ghost is, if it's in the beginning, the ghosts have a subspeed they have a base speed that's 0, and it's more the fractional portion that's determining how fast they are, because when Miss Pac-Man starts her first stage, she has a base speed of 1, so you want that base speed for the ghost to be just slightly slower than the player. So in the first stage, at least, the Miss Pac-Man is 1, so that she can move 1 pixel per frame, whereas the ghosts are fractional, so it's 0 for them in the beginning, and it all goes by the fractional portion, which is the entity subspeed. So we would set the entity subspeed to a certain level, and what this does is, this is the actual current accumulated subspeed, and what we're going to do is we're going to add that subspeed constant, or that we set for, it's not a constant, but that variable that we set for the entity, and we're going to add that to the current accumulated speed, which again is a unsigned car. So we're going to keep adding it here and then we're going to get this accumulator, which is going to be short because we're going to have to check if it's greater than 255. If it's over 255 in this scenario, then we're going to add 1 to the speed, saying that this is how much we added during this accumulative call. So, and normally this would be done easier in assembly. Assembly has flags for the registers, and I think one of the flags is an overflow flag. So in the assembly portion of it, if we would add this accumulated score and it would go over 255, there would be a flag that we could check here instead of doing this in a more inefficient manner. We would just check that flag, and then if that overflow had occurred, then you could do a quicker conditional on that. Whereas I'm making a short here, it's probably not the best approach to this. So I just want to give some background there and where things would be more convenient if you're using assembly versus maybe something like this, or maybe there's a better approach to this, but this is the approach I took with it. So if we know that overflow, that means that our accumulated subspeed has overflowed the 255, and that we can add something to that speed increment. So, and that's what we do here. We increment it by 1, and then the accumulated subspeed we update with the calculation that we made here, and then we return that speed to the calling code. This one, check entity collision. So this checks for collisions with the players. So, and it would be called by the ghosts, and it would be called by the bonus entities. So if we're in team mode, we're going to check for both player 1 and 2. And then so how would we do that? We were going to check the given entity. So what will go in here would be the entity that we're checking the collision against the player. So it might be a ghost, it might be a bonus, whatever. So that's what this index would most likely be. So we would check the entity tile. That means the tile index that it's currently at. So it would be this number, the actual show tile, the index. So it would be the index. We're going to check if the tile index that the entity is on is also the same tile index that the player 1 is on, and we're going to check if those match. If those match, then there is a collision, and all the collision in this game is done per tile. Isn't a pixel perfect collision system, so is a tile based or tile driven collision system, which is a little different, a little bit more simplistic, but also has its own pros and cons. So we're going to see if the player and the entity that we're given is the same tile. So we're going to check it for that entity tile in player 1, and we're going to check the entity tile of the entity that was given. And then there's also, we're going to check the previous tile that the player was at to give it a little bit more. If you don't do that check, there's chances where the player can pass through the entity in question, or the given entity. So it could pass through a ghost, or it could pass through a bonus item, depending on how when the collision is checked here versus the position of the player. So we're going to check not only the entity tile that the player is currently on, but we're also going to check its previous one from the frame before. So we're going to check those. We're going to check if it's on this or the previous one. If it is, then we're going to return the index of player 1, saying basically, okay, we collided with player 1. And then we do the same exact check here, but we do that for player 2 instead. And then if these two do not have any condition where it's true, then we're going to return a value of 0, saying false, we didn't hit anything yet, or the entity didn't hit the player yet. So that's all that's doing here. Very simple collision detection. And then if the player mode is player 1 or player 2, we're only interested in looking at the current player that's playing that stage. So it might be player 1, might be player 2, but it isn't in a team mode. So, and we only have to check one player, which would be the current player, instead of this, which we'd have to check both, because they're both on the screen at the same time. Position the tile. All this does is, there are times when we want to check the raw pixel position of the entity, both the horizontal and vertical position, and that would, again, will be stored in under globals. If we go up to the entity X and the entity Y, this is actually a short, which is an actual value that is the pixel value, or the pixel position of where the entity is. And we use that typically when, well, for everything, is the origin of the player. So this is the actual origin position of the player, where everything else is based off of. So when we go to draw the sprite for the entity, this will be used as part of the calculation of where to draw the sprite. It will be offset from the center of the origin in most cases, but this is the actual pixel positioning of the player as they're going through this stage, and we kind of see that here. If I hover over this, you can see that there's some values here, and the ones that we're interested in is the Y here and the X. These are the actual pixel positions. So if I hover over this, the actual pixel position here is Y is 256, but it would be a little bit more because we want to get the center part, and then that would probably be about 260 where the player or the entities actually lie. So it's just a little bit more than the maximum value of a car. So otherwise we could just use car for these instances, but we are using a short because of the way that the maximum value is for the entity. So unsigned short here, which is a little wasteful, but it is what it is. So all we're going to do is take those pixel values, and then we're going to use some arithmetic here to get the actual position, the tile position. So that what we're interested in is, when we're hovering like over this, it says that our position 72 by 280. What we're interested in is taking these two numbers here, our raw pixel positions, and getting this value. So this index here, the 1129, that's what we're interested in getting. So in this scenario, so we're going to take 72 and 280. So let's grab our calculator. And what we're going to do is this first, here, let me move this over just a tad bit. We're going to take our y, which here in this scenario is 248. Looks like I'm changing in all kinds of places. Let's take 256. So we're going to take 256. And if you recall, when we shift to the right, we divide by a power of 2, and that power of 2 is 3 here. So what does 3 mean? What's the actual number that we are going to divide by? So let's take a look at that. That's going to be under, what am I looking at here? Power of 2. So if we have 3, that's the actual bit that we're going to shift by, and that value is actually 8. So that we're dividing by 8 essentially here. So we're going to divide by 8. That's going to give us 32. And then we're going to now times it by 32, which that's what 5 means here. So our bit for 5 is 32. Is bit 5 is 32. So now we're timesing by 32. I mean, yeah, dividing by 8, and then we're times it by 32. So I got 32, and we're going to times by 32. So we have 1024, and then we're going to add whatever x is times 8. So that should give us our value. So if we go back into here, wherever one I picked, that position x is 64. So we're going to take 64 and we're going to divide that by 8. I don't know if it said multiply. I meant divide by 8. So that should give us our value there. So we have 1024. We're going to clear that, and then we're going to take 64, divide that by 8. And then we're going to add that previous 1024. And that says it's 1032. And there's our number for that. 1032 would be the resulting number from that arithmetic. And that's what we're looking for, because there are times when we need to convert our actual pixel positioning to a tile index. And that's what this calculation does. And the reason why we use 32 in a lot of these calculations, and I know I didn't bring this up before. First of all, we bring power 3 is 8, so 8 is obviously the 8 by 8 pixel blocks, so that's why we use that number. And these, the vertical positioning and the horizontal positioning. And the reason why we use 32 is block positioning for the amount of blocks that the game has. And we have to use the width of it, so we're using the width of the actual map. If the width was bigger, it might be different, but here we're using the entire width of the game screen, which is 32. So we're actually, in this part of this calculation, we're taking in consideration the width of the map itself as part of that calculation. So this would be different depending on how many tiles you had width-wise, and in this case it's very simplistic, and we're using the 32 tiles that the Sega Master System allows by default in mode 4. Okay, now we're going to move on to the next one. Position to tile offset. So this is used primarily by the entities that don't have the ability to corner cut. If you recall in one of the previous tutorials, one of the features that the player has is the ability to cut a corner faster than the ghosts can cut the corner. So the ghosts have to move all the way to dead center of a tile before it can move to another tile. So it has to go all the way dead center to the center of its origin, and then from there it can make a move only when it meets that center of that tile. So what we're doing here is we're going to get the same thing that we've basically done here, but instead we're going to offset it just a little bit to the center of each tile that it's entered. So everything's 8x8 pixel blocks in the game because that's naturally how the Sega Master System handles its tiles. They're all 8x8, but we actually want the actual center of those 8x8s. So we would get the 8x8s, but then we also would offset just a little bit so we can get 4 pixels in from the top and 4 pixels in from the left. So it would, so when the direction is down, we're going to offset it by 4 in certain scenarios, and then we're going to add it some scenarios where we're going to add 3 pixels to that, just so we can get the center portion of the current tile that the ghost entity will be in. And this also applies to the bonus entity. It's just the same thing as this, but we're offsetting it just a little bit so we can get that center. And we would do something similar for the player, but since they have the corner cutting ability, they don't have to be dead center before they can go into another direction. Here, these entities have to be dead center before they get into those scenarios. And you can see it's essentially the same thing as this, but we're going to take whatever our given entity is at this point, and we're going to, since it's down, it's a vertical orientation, so we're going to offset that X that that Y that we normally would get here. We're going to offset by 4, and then we're going to do the same calculation here where we're dividing it by 8, and then we're timesing it by 32. Same thing here, and then we're just adding that same portion. But again, this is by the entity that's given. So here, typically the index given would be the ghost entities or the bonus entity, and then we would figure out what direction that they're facing, and then we would adjust the tile index that we would given it back just a little bit for those entities, and that's all this does. So typically that's what, instead of using this position of the tile, which what a player would use, this is what the other entities would use, because again, they have to go dead center into those tiles before they're able to make another move in the desired or the calculated direction. So, and everything revolves around the facing direction of the entities that are given. So we're just doing a check on which direction the entity is facing, and then we have case statements for all that, and then we have the default one, which is typically the right direction. And as you can see here also that we're giving back that tile index, and it's a short. So here we're kind of doing the reverse of this. So instead of giving it or looking at the pixel horizontal and vertical values, here we're actually handing it the tile index that entity may have. So here we're giving the index of the entity because we're going to actually change the pixel position of the entity that's given here. So we're actually going to be setting some values, or its properties, X and Y property, based off of the tile index that we give it. And here we're just doing a breakdown of the tile index so that we can get the X and Y positioning off of it. So here we're taking the tile index and we are dividing it by 32. Again, if you recall, 32 is the maximum width. So if this map was not 32, it would have to be a different value here. Conveniently, it's 32, which is a power of 2, which is nice. So we don't have to do anything with the multiplication that's outside of that, or division that's outside of a power of 2. So we're going to use that 32. Convenient. We're going to get a row, and then we're going to again calculate the actual X position tile wise. So, and that's going to require again that we're going to, much like this, we're going to take that 32 from the current row we have, and we're going to times that by 32, and that's going to give us a raw pixel value for the Y positioning or the vertical positioning. And then we're going to subtract that from the actual raw tile index that was given. And then at the very end of it, we're going to times that by 8. So this will give us the positioning that we want, and then we're going to, which will be in tile form, and then this will actually times that value by 8. So that's the raw pixel value you have for the horizontal positioning. And then we can also take that row and then times that by 8 for our raw Y pixel positioning. And that will set up that conversion from the tile index, which would be a single number, and break it down into these two values for the X and Y. And where I typically use this is I will use this when a bonus appears on the screen. So there are typically four different, oh, not typically, there are 4 different places that a bonus can spawn on the stage, and it is randomized. So first we randomize 4 different places that the bonus could show up, and then we use this function to take a tile index that is hard-coded in for the bonus, and we convert that to where it would actually be on the screen. So this is where it typically be used. It won't be used in the actual game loop or the engine loop over and over again. It will just be used once on load. So this is not that intensive when it comes to the processing. Here we have entity can move, so we're going to check if an entity can move in a certain direction. So first we're going to give it the tile, so that tile index. So like in this scenario, let's say tile index, and I think I pointed the wrong one in one of the previous tutorials. 847 here. So let's say there's an entity here at 847, and then what we're going to do is we're going to look in the direction that's given in the argument. So it's going to either look from 847, it's going to look up, left, right, or it's going to look down. So, and how that's handled. So we're going to give it the tile that we're looking at, that tile index, and then we're going to look for the direction where we want to check if it's a solid tile or not. So here, depending on what the direction, so say we're looking at a tile index and we want to look below the tile index, or here, let's say that we want to, so you want to look below, the direction is down, and we want to check, okay, is the tile below us, is it solid? So how does it do that? We make our get map tile ID, which is off of the, I think it's up in common here that we have that. We're going to check the current player's map data, and we're going to check, okay, at this tile that we're given, which would be the tile that a entity currently sits on typically, and then we're going to check, okay, right below the entity, can it move down, or is it a solid down below? So how do we do that? So whatever our tile amount is here, so we're going to have 4, and 847 is here. We're going to check into the tile below us, which is 879. So how do we do that? So we take the 847, and since we know the width of our map is 32, which is very important, we know it's 32 tiles from one and the other. So all we do is going to add 32 from here. So 847 plus 32 gives us 879 here. So this is essentially checking below at this point. So in our theory, and in this example, so here then we add plus 32. It's going to check the current player's map for right here at this index, and it's going to check, okay, what is that tile ID underneath there? And then we look at the tile ID underneath there. It's 343 is the tile ID. So get map tile ID is going to spit back the ID and this given index, and then we're going to check, okay, is it greater than our tile, our solid tile beginning point, which here is 340. And then when we checked it, as you may recall, it is 343, So in this scenario, this tile ID is actually greater than our tile solid offset, or where our cutoff is. And then this is basically saying, okay, this tile is a solid tile. And then again, we're doing a shorthand here. So it's like, okay, we're checking, is it greater than where our threshold is for a solid tile? This is the question that we're asking. And if it is greater than the tile solid, we're going to return false, meaning we're asking the question here, can it move? And we're saying 0, no, it can't move here. That's what we're returning. If this wasn't true, then we'd return 1, saying, yeah, the entity can move there. So we'd hand back a 1 in this scenario. So here we're asking, can the entity move at the tile that we're giving in the direction that we're going to check? So that's all this does. And then typically when a ghost gets into an intersection where it can move more than one direction, it will check all the available directions to it. Once it gets to the intersection, it's going to check if it can go up, it can check if it goes down, or that sort of thing. It'll actually check all 4 directions in that scenario, and all scenarios should say it will check if it can move in a certain given direction here. So typically it will check all 4 directions other than the way that it came from, typically, because it can't move backwards. But it'll check those positionings there, and then it'll do an action based off of those results coming back, whether we can move into a certain tile or not. So that's all it does here. Move entity. Again, this is typically what a ghost would use or a bonus item would use for its movement. And all we do is give the index of that entity. Again, we're going to change the X and Y depending on the direction that we're going to move the entity. So we're going to get the speed first. Again, we're going to accumulate that subspeed for the entity that we're going to change the positioning to. Again, that can be, in this scenario, it would be ghosts and bonuses. So we're going to get that speed. Then we're going to check the direction that we are going to move that entity, because by now we have already checked if we can move in a certain direction. Here we're all actually going to move that entity in that direction. So we're going to check which direction we want to move in, and anything that has to do with right and left are going to affect the horizontal positioning or the X positioning, and anything that moves up and down will affect the vertical positioning or the Y position here. And you can see here we're going to take that speed, whatever we get, and we're going to apply that to the X and Y positioning of an entity. And if we want to move right, as you remember, when we move right, when we move this way, we're actually incrementing the X value. So as you can see down here, the X, as I move it along, it will increase as I go. So that means we're moving right. If I go left, it decreases as we go. And the same thing for the vertical position. So as I go down, I'm increasing the Y, as you can see. And as I'm going up, I'm decreasing the Y until it gets to 0. And that's the same kind of behavior you have here. So I want to move to the right. So since moving to the right means that I'm going to add that speed here. So all this says is I'm going to add whatever the speed value is to my entity's horizontal position. Same thing for this. Since I'm going down, I'm adding. So we're going to add the speed to the vertical position of the entity. And here, when we're going left, we're actually subtracting towards 0. So we're going to subtract, and same thing with the vertical position. If we go up, it's going to subtract. So we're going to subtract that speed for those values. So that's all we're doing here. So based off the direction we're given, we're going to adjust the positioning of the entity that we're given by the entity's speed, accumulated speed at this point in time in the game. So that's all we're doing. Entity stat tile. This is again for the entities that have to move on the grid, and they have to be specifically in the center of the grid. Since the entities, their speeds are fractions, they don't always line up perfectly on the grid. Like if we did whole numbers, as in we only used like 1 or 2, we could definitely we wouldn't need any sort of adjustment to them. But since they move in a fractional amount, they may be in certain scenarios where they're just over the center of the tile that they're in. So when they go to change into that tile index, this will adjust it that it snaps that entity, its Y and its X positioning to the center if it's just a smidge over. And this will be called only when there is a tile index. So there's two properties that we have already discussed: the tile index, the current tile index, or the current tile that the entity is in. So we would have this, that'd be our current tile that it's in, but we also keep track of its previous tile. And the only time that we're going to snap it towards the center of or we're going to make that check to see if it's in the center of the tile, is when these don't equal each other. So that would happen every, say, 8 pixels of movement if the entity is moving, which all the entities are typically moving. So we're going to check, okay, if these don't match, then something needs to update. So we're going to update check its collision detection. Is going to check the next tile can move in, a whole bunch of things. But so here we're just going to call this when there's a change in tile. It does then at that point, if it's just checking if it's a horizontal direction. If it's a horizontal direction, we're going to snap its vertical direction to the center of the tile. And again, that's some small arithmetic. We're going to take whatever its entity Y, its vertical position, we're going to divide that by 8, because again, it's 8 by 8 grid. And then we're also going to snap it to, we're going to take that value, and we're taking this value, we're going to divide it by 8, so we get that tile amount, and then we're going to want the pixel amount. So then here we're timesing it by 8 to get it into snap position. And then once that's all done, we're going to snap it to the center of that tile. That's where the +4 comes into play. So when it's going left and right, we want to make sure that we snap to the center on the vertical position. And if it's not going left, right, then it's going up and down. So then we want to snap to the horizontal position, if that makes sense. So it will be snapped to its X position. It's just snapping it to make sure visually when the ghost is going through those tunnels, it's not offset by, a pixel or two based off of how the fractional portion of the entity is being calculated at that time. Because it may be over the center when it goes to make a change in direction. We want to correct that behavior, and that's what this does. And we call this, again, when the previous tile and the current tile don't match up, then this is where we would call this. And then whatever that entity's current direction is will snap in the opposite axes. Check rep. Here's when we do that. Check if there are a certain position, the entities, any entity, whether it be bonuses, ghosts, or the player, if they reach a certain part of the screen in there, we're going to take whatever the position is there on the X, because that's the only thing we're worried about is the horizontal position. So when they go through a tunnel over here, once they reach here we're looking for, okay, is it less than 8? So if their horizontal position is less than this last tile here, what it's going to do is it's going to push them all the way over to this side to make it look like they're traversing through here from one end to the other. And why do I do that? Because typically you wouldn't have to do this. It would just automatically do that. It would do that overflow, and in a typical Sega Master System game, you just go through and you end up on the other side anyway. The reason why we do this is because of the way I calculate the tile index. If the player is less than the last tile or whatever, the way that I would calculate the tile index of where it's at would be incorrect. So here we're going to mitigate that issue by just saying, okay, if it's less than that 8 pixels, we're going to magically push it all the way over to the right at this hard-coded value, which is 240 pixels. So when it comes in here, player, entity, whatever it may be, bonus, well, bonus typically, that wouldn't matter. But ghosts and the player, once it gets that the horizontal origin point is less than this one tile, it will automatically push them over at 240 over on this side. So, and that's what we're trying to do here. You see where 240 shows up, it's right about here. So since the center of the origin of the entities are typically here, it'll be set at this point to come through. And as you recall, we made this that it would draw over top of the player and other entities, so it'll make it look like we're coming from the other end through the tunnel. So we're wrapping over. So that's all we're doing here. So we're checking it for, okay, is it less than 8? Then we're going to put it here. If it's greater than 246, well, then we're going to, so this is essentially saying if it's too far to the right, we're going to wrap it to the left. That's all this does. So again, it's just given the entity index that we want to change, and then all we're doing is changing the horizontal positioning of the given entity. Here we have a constant array. These are, I put this here because I wanted the data to be as close to the next method that we're about to go over, which are our next function that we're about to go over, which is also our last function for this source. So number squared, what is this? So as I've said before, natively the Z80 hardware wise doesn't handle multiplication and division. So the ways around that are you can either roll your as quickly as possible software implementation of what multiplication and division may be, and I'm sure that's what SDCC provides. But there are other situations where those arithmetic operators are just going to be too slow regardless of what the best things that SDCC can do for you. The compiler is just going to be slow. So there's going to be a calculation coming up that we're going to go over that I need numbers. I need the power of 2 or the squared version of a number. And if I would do that using the arithmetic through SDCC, no matter how good it or optimized it tries to do that calculation, it will just be overall slow. So what we can do is pre-calculate these numbers, and that's what this table is. It's a pre-calculation that I can use later, and there's not a whole lot of elements to it, so it makes sense to do in this scenario. So one of the things that we need to do in the game is that we need to figure out, depending on a certain tile, we need to look at one tile, and then we want to also check how far away it is from another tile, right? So in this scenario, and this is given by Retro Game Mechanics Explained, and this is where I got a lot of the information for Miss Pac-Man. Without it, I probably would be a little lost on some of the behaviors of the game. So this is also where I learned that the R register was used by the mod team for Miss Pac-Man, which I can't remember the actual company name. Forgive me for that. But in this scenario, Retro Game Mechanics goes into detail saying once we reach here, like in this scenario, we have a ghost, and the ghost needs to make a decision based off of the valid directions it can go, and needs to take that tile into consideration. So it's going to, here in this scenario, it can't go back because that's part of it can't go backwards as part of the rules of the game. Instead, the only ones are, and if you look, so remember that whole thing I did with checking all the directions for a ghost. So it's going to check here, check here, check here, and check here. It's going to find that this is solid, so it can't move there. It can't move backwards because we're already going left, so the opposite direction would be right. We can't go that way. So the only two available options is this one to the left and this one down here, and the target is off screen. Again, this is part of when the ghost is in its non-chase state. It's in the state where it's kind of idling until it switches over to the chase state. So it's trying to get to the target. It will never get there, but the idea is that it's going to keep going around this loop over here until it goes in the chase mode. Then it's going to go after the player. But we need to know what the shortest distance is to this target. So we're going to check from the tile below to this target, and we're going to check to the tile to the left to this target. And as you can see, there's an equation here that is given that will give us that information. And as you can see, part of that equation is this power of 2, or a squared value based off of tiles. So here it's looking, I think it's 5 tiles to the left, and then, or horizontally, and then 8 tiles vertically to get to this target. So that's why it has an 8 for the vertical value, and here 5 for the horizontal value. But if we add 8 plus 5, that will give us the same value as 7 plus 6. So it would essentially say that it would be equal. But there's another facet to this calculation, in that we need the power of 2 for it, or we need it as a squared value. And we're going to do that pre-calculation in this table. And that's the whole reason why we have the table. Because if we would do this multiplication, 8 times 8, or 8 to the whatever power, there's available libraries to do that within C, where we can take the get a power of a number. It would still take too long, and it would absolutely destroy the performance of the game. So we're going to pre-calculate those in advance, and I'll show you what that means. So no matter what number we give it, we're going to get a squared value back. So if we hand it 0, 0 times 0 is 0. It'll always be 0. If we hand it 1, 1 times 1 is 1. If we hand it a 2, 2 times 2 is 4, and 3 is 9. 3 times 3 is 9, and so on and so forth. So that's what we're doing. It's the only value. So if we hand it a value, it will give us the squared value, or the power of 2 value for that numeric that we give it. So, and we're going to go in order, and we stop at, I don't know if it's 36 total elements. Why do we stop at 36 elements? Remember, these are tiled values. So when we come in here, the highest tile value that it could possibly be, if we hover over it, is 35 here. Remember, it starts at 0. So 0 to 35 is 36 values altogether. So the highest it could ever possibly be is 36, because our map is finite, and that is the highest value it could possibly be. And when we do horizontally, it's only the highest value you can do through it horizontally is 31 or 32 values altogether, because remember, it starts at 0. 0 to 31 is 32. So we know that the highest that it could ever be is 36 values. So that's all we're going to put in here. We're not going to put any more. We don't need it, because we should be covered by just giving it 36 values. So that's what we're doing here. So we're going to give it up to 36 values, and then, we can look at this value. You take the maximum, 36 times 36. It's going to give you, oh, I'm sorry, because it's 35. 0 to 35, sorry. 35 times 35. And that's going to give you your 1225. So, yeah. So that's what we're going to use. These are pre-calculated squared values, and this is way, way, way faster than if you would tell the Z80 to do the same thing on the fly. So we're going to save ourselves some processing power by doing this. Then the final function of this source is get distance. This is exactly the thing that I just showed you. Now, I'm going to make another announcement about this. this is performant code. This gets called quite often throughout the entirety of the game. What I'm doing here is, you shouldn't do it this way. I know I'm showing. I did this for breakdown purposes and to show some other things with it, but typically you do not want to make 6 local variables here. You want to try to keep it as slim as possible. If at all, you want to try and not have any of these in here, except from what I understand, maybe to define an index, or like if we're going through a for loop or something like that, or some other sort of thing. You typically don't want to do that. Although there are times when I have tested this in real scenarios where having one, if it's a value that keeps getting used throughout your code, actually seems to be a little bit more performant actually. And it's not always the case. Most of the time, this rule that I discussed here holds true. You should only have maximum of 1 of these local variables, so ones that are within the scope of the brackets here and isn't a global variable where we define it. You should only have 1 maximum. Typically, that's how it's said. But again, there's times, and I'll get into that. When it comes to the player, when I manipulate the sprite, it is actually quicker to define 2 local variables versus me constantly going into the global for whatever reason. I have seen some decent kickbacks when it comes to that, and everything I go over through and I look at it is on a scan line basis. And again, I'll show you that once we get into using Emulicious and we're looking at our performance and all that sort of thing. We haven't gotten there yet, but trust me, we will get there. When I look at those metrics, sometimes it is actually quicker to define those local variables in certain scenarios, but typically you want to keep it low. And here I'm actually using 6, which is blasphemous if you want to look at it that way. So typically you don't want to do that. And this is one of the most intensive calls in the game, and we're only doing a little bit of arithmetic here. So, but I just want to preface that on some of the things that you should kind of get in the habit of doing, and knowing that, hey, you can't use this many local variables within your function because it may affect performance. And same thing with these arguments. You want to try and keep it, if it's code that we're constantly looping through, you want to try and keep it to 2 or less for the parameters. But if you're loading data and the performance does not need to happen there, you can add a bunch more parameters, and you'll see that. Like when I go to set up the player, or when I go to set up the other entities, I actually have quite a few parameters coming in, and it's more acceptable in that light because again, it's not the game engine running where you need to have it performant so you can avoid lag and that slow down and that sort of thing. So all right, let me get into this. So the 2 arguments that we're handing in here is very much the same what I just discussed off of the video that I was showing that graphic from. So we're going to hand it the source tile, or the tile, the tile 1 here, so the source tile, and then we're going to hand in the destination tile, or these are tile indexes. So we're just looking at 2 numbers coming in, and what we will do first is we're going to break it down into the X and Y, so the horizontal and vertical tile breakdown. So what does that mean? So if you give it an index of, again, we're going to go back to 847. So if we give it 847, you can see that the tile X is 15 and tile Y is 26. And that's all we're doing here. We're going to break that down to those 2 tile X and Y's. And then we're going to take our destination index and we're going to do the exact same thing. We're going to break it down to those amounts. So let's do a scenario here. So this kind of makes sense. In our video here, when we look at it, the ghost is sitting here and this is trying to get to this target over here. So that's essentially, they're on tile 840 at that point. And they're looking to either go to this one over here, which is 839, or they're going to try and go down here, which is 872. So these are the two options it has. Can't go up to 808 because it's a solid, and it can't go backwards as part of the rules of the game, is that it has to constantly move forward. It can't change direction unless the ghost is frightened or the chase state changes at some point in time, which is on the timer at that point. So in this scenario, we're going to both check. We're going to check 839, and then we're also going to look at 872. So if we look at those two numbers, you can see that the breakdown for 839 is that the tile X is 7 and the tile Y is 26 in this scenario. So that's our first breakdown we're going to do here in this code. So we're going to take whatever our tile ID is, which we said was 839, correct? So 839, that's what we're going to hand it. And we're going to try and get the Y positioning tiled. So we're going to divide that. Remember, if we go to the right, we divide by the 5th bit. And if we look back at our table, the 5th bit would be 32 in this scenario. So we would divide it by 32. And that will give us 26 for our tile positioning. So if we go back over here, you can see tile Y is 26. So there we got our vertical positioning tiled. Now we want the horizontal positioning tiled. So what we're going to do is going to take that 26 that we just got, and now we're going to times it by 32. I don't know. Doesn't really make much sense, but so then it's 832 at that point, and we're going to subtract it against the tile ID they were given, which was 839, if you recall. So 839, we could put that in there. I think it's 839, right? 839, and then we minus that by 832. That gives us 7, which is exactly what that says at the bottom there. Tile X 7. So now we're getting that 7 and we're getting that 26, just like it's already done for us here in the SMS Tile Studio. So we have that breakdown, so 7 and 26, and then we're going to get our target tile, which would be, in this scenario down here, we're trying to get to, well, let me zoom in here because it cuts off the index. We're trying to get to 1090 is what we're trying to get. So in 1090 here, it tells us that our X position is 2 tiles in and the Y position is 34 tiles down. And this should be the same thing. So we take 1090 and we divide it by 32. Again, the width and tiles of our map is 34. So if we hover over it, it says 34. That is correct. Then same thing. So we then times 32. And that's 1088. So we'd start here, 1088 to 1090, which is our what we would subtract by, because tile 2 is at 1090. If we subtract these two, it would be 2. And again, tile X 2 there. So just to show that, it would be, we'd then take 1090, and then we would take that the 1088 and subtract it, and that will give us 2. So that's where these numbers are coming from. 2 tiles in, 34 tiles down, or to the right and down. So that's where this calculation is. It's going to break those values down, and then here we're going to check which one's bigger before we subtract our source against our target or destination tile index. So you could do this another way. There's the math functions that C gives you. They have something that's called absolute, or where you can change a value. If it has a negative, it would be a positive. It will always make it into an absolute value that's a positive value. I'm not going to use that here. I'm just going to use some quick ternary logic. So here we're just going to check, all right, is our source tile, the horizontal or the X of it, is it greater than the destination? If it is, then we're going to subtract, because X1 will now be the bigger number. I'm going to subtract it by our destination X. If it's not, then the destination tile is the bigger number, And so we're going to subtract it like this. So again, here we're asking that conditional question. Is our source tile horizontal position, is it bigger than our target tile or destination one? If it is, then we can just use this here, saying that the source tile actually is a bigger number than the target tile. So we would subtract that way. That way we don't have to worry about a negative value at that point, because that we don't want a negative value. You want just the actual raw distance of the target tile and the destination tile horizontally here. So we just want a positive number. So that's what we do there. And we do the exact same thing for the vertical position. Again, checking, is our source tile, is the vertical position bigger than the destination or target tiles vertical destination? If it is, then we can safely make that call here. If not, it would do this. And obviously if it was equal, it wouldn't matter. So it would just zero out at that point. I don't know if there's ever scenarios where that happens. Probably. I don't know. So then once we have our X and Y difference and what these numbers would actually calculate to. So let's take a look at that real quick before we move on to the last thing here. So when we would take those numbers and we subtract them, so let's take a look. So in our destination one, we'll do X first. So our destination one, which is 839, our source tile here, 839, we're going to look at the X. Tile X is 7, and then the one down here is tile X is 2. So whatever the bigger number is, as per what we just did here, it would be subtracted by the smaller number. So 7 take away 2, X would be 5 in this scenario. And then for Y, when we look at that, we look at our source tile here, which is 26. Our destination is 34. Well, our destination tile is actually bigger at this point. So then we would take 34 and then subtract 26 at that point. And we can take a look at that one. Take away 26. It's going to give us a difference of 8. So that's what this one would hold. That's what these two values will hold there. So, and then we would take those values and then we would put them in the table based off this, and that would give us a number. So again, going here, they did the same thing. We got an 8 and there was a 5. So a 5 and an 8 based, that's where our calculation is here. At this point, our horizontal position is 5, and at this point is 8. And then what we're going to do then at that point is we're going to plug them into the table so we can get the value that would be the squared value. So I'll go through that right now. So since X is 5, so we're going to go and plug in 5. 5 times 5, because this is an index, so we would plug in 5, it would be 0, 1, 2, 3, 4, 5. So it would end up here, it would be 25. So this is going to hand back 25. And then our other value is 8. So if we do that, 0, 1, 2, 3, 4, 5, 6, 7, 8, we'll go to the eighth element in this, it will hand back 64. So it's going to hand back 25 for the X value, and it's going to hand back 64 for the Y value. So, and then if we add those two numbers together, that will give us our distance. So again, if we look back at the video, it says 89 here. So, and we do the math here. So we remember it was 25 for the X value, and it was 64 for the Y value, 89. And that's the same calculation to get here. And it would be the same thing for if we go down, it would give us 7 and 6. And then we can look in that table to get what our squared value is, and then it will give us 85 back. It's essentially doing the exact same thing the game did here. And that's how this arithmetic is done, and also why we have a table of already pre-multiplied values at this point, so, or squared values at this point. So, and that's, hopefully that makes sense on how that works and why it is the way it is at this point, and why there's a breakdown, and why I wanted to show you how to do this in this fashion. There are other options that SDCC allows that you don't have to do so much arithmetic here, but I just want to show it in its more raw value. raw way of doing it, and you can even create macros and other things that would do this in a more simplified way. And I think that's everything. So hopefully that made some sense, and hope you enjoyed this lesson, and I will see you next time.